Hello and welcome to another live stream from Portland State University's Learning Center. This live stream is where we're going to be covering Physics 232 topics, specifically potential energy and voltage potential. So first, a few bookkeeping things. I'm going to post a few links in the chat for anybody who's watching live. These are useful links for the resources the Learning Center has for you. So there is the Learning Center's website there. They have a lot of useful links and tips. So you can schedule tutors online. You can go to academic coaching and other things like that. You can also follow the Learning Center on Facebook and Instagram. And you can get live updates of whenever they add new things or new ideas that they have to help out the student population. Also, this is for Physics 232, and there's an attendance sheet, which is a Google form. I'm going to paste the link to in there now. So make sure to fill out that form if you're here and get extra credit from your teacher for doing that. I'm going to place that link as well at the end of the term or end of the session. So if you miss it at the beginning, you'll have it there. So let's get started. We're talking about potential energy. Potential energy, just like what we had with gravitational potential in mechanics, is basically the amount of energy that's possible if you kind of just let everything go loose. So in mechanics, we talked a lot about like gravitational energy and gravitational potential. So if you lift a rock up in the air and you let it go, it's going to fall, and it has the energy to fall, and that potential energy turns into kinetic energy falling down. Similar things happen with electric forces as well, where if I have 2 point charges and I let them go, they're going to, if they're this different charges, they're going to be attracted towards each other, and they're going to start seeing that potential energy turn into kinetic energy as they move forward and towards each other. So the same charge, either both positive or both negative, they're going to be repulsive force. They're going to be pushing away from each other. And so essentially, as they start to move, that potential energy turns into kinetic energy, and they start to move away from each other. Obviously, the amount of force changes depending on the distance. So as they get farther and farther away from each other, that force becomes smaller, and the rate of acceleration decreases as well. Excuse me. The opposite way, if they're attractive forces, the forces are going to get larger and larger the closer they are, until eventually they finally hit, they combine together basically, and they've reached the maximum potential energy they can have. We like to say, if two charges are as far apart from each other as they can, if the distance between them is approaching infinity, their potential energy is zero. And that has to come off of the idea of the force equation, right? So the electric force, as we went over before, is equal to K QQ over R squared. And so that force at a distance of infinity is pretty much zero, because as R approaches infinity, the force itself approaches zero. As R gets really, really close, the force is really, really strong. So the potential energy is really great at that point. For potential energy, we can say that the work done is equal to the change in potential energy. In this case, the work done to accelerate a positive charge from rest is positive and results in a potential energy or a negative potential energy. In this case, we can say that the potential energy at any point is going to be equal to KQQ over R. And notice the difference between these two formulas is simply that we've taken out an R in the denominator. The change in potential energy is equal to the negative, and we'd have to go into a bunch of calculus to prove that, basically. But really, it's the idea that the work done on the system is equal to the negative of the potential energy, or the change in the potential energy. And the change in the potential energy would be equal to the negative of the work done. And that it's based on the distance it has to travel, whether it's towards infinity or coming closer together. So a simple way to remember is the electric potential energy is positive if both charges are the same sign. So if I had two charges here, and this was a Q, which is a positive charge, this is Q with a positive charge, they're going to have a repulsive force pushing away from each other. but the potential energy for them are going to be positive, because whatever that potential energy is going, as the forces start to act on each other, that potential energy is going to get smaller and smaller, or to zero essentially. So if they both have that same sign, it's a positive potential energy. If they both have a different sign, like one's negative, one's positive, okay, then they're going to have that attractive force. Okay, they're going to be pulled towards each other, and we can say that the potential energy in this case is negative. Okay, because as that force applies, the potential energy is going to increase. Okay, we're basically putting work into that system, because the distance from compared to the zero potential, which would be infinity, is getting bigger in that case. It's a little bit different than gravity in that way. So if I had an object, like I have a screwdriver here, if I set this object on the ground, so it's lying flat on the ground, it has, we could say, zero potential energy. It can't fall from the ground, right? But if I lift it up in the air, we've then done negative work. We've added it into the system. So if I drop it, it turns into kinetic energy. It has that potential and it goes down. Okay. In this case, by pushing it up into the air, I've done negative work on it, and then gravity does positive work pulling it back down. So something similar is happening here, where two charges that are opposite signs are going to do negative work on the system, pulling them closer together, and two charges that are the same sign are going to be pushing them farther apart, doing positive work on the system. Yeah, we have a positive potential energy on the system. And as always, there is a conservation of mechanical energy. So what I mean by conservation of mechanical energy, it all comes down to mechanical energy. The idea that the kinetic energy plus the potential energy is always conserved. It's always a constant value. And we can use that. So if we say the kinetic energy initially plus the potential energy initially should equal the kinetic energy of the final part of the system, so after the change, plus the potential energy of the final part of the system. So when it starts, if something starts out at rest and it has a lot of potential energy, at any point in the future, we can see that as that potential energy is used up, the kinetic energy goes up, and it compensates for it. So the sum of these two on both sides of the equation should be the same. This is going to be equal to this. And that's going to be true with everything in physics, always. It's a universal law of physics, is you always have this conservation of energy. So let's try this on a problem now. We're going to calculate the potential energy of a hydrogen atom. The electron and the proton rotating around the hydrogen atom there. So we want to calculate the potential energy of the electron and the proton in the hydrogen atom. And we're going to use 1 EV is equal to 1.6 times 10 to the 19 joules. So that's a conversion factor. We want to find its potential energy in EV. When we get to really small scales, EV is a lot more useful. So we can do that using the idea that the force is equal to K, Q of the electron, and Q of the proton divided by R squared. And the idea that negative work is equal to that K QQ over R, which is equal to our change in potential energy. So to find the potential energy, we really need to say, move that negative sign around, negative KQQ over R. So we know the charges of the electrons, we know the charges of the protons. They're actually the same charge, just one's positive and one's negative. And we don't really care about the charges, we can take the absolute value of those. So that's going to equal negative K times 1.6 times 10 to the negative 19 coulombs, all squared, because we're just squaring that charge, divided by the distance between them. In this case, they say here the distance between them is 5.3 times 10 to the negative 11 meters. So we can say it's 5.3 times 10 to the negative 11 meters. And if we plug that into our calculator, using this value for K of 9 times 10 to the 9th Newton meter squared per coulomb squared. Let me start a new calculator. So that would be 9 times 10 to the 9th power in units of newtons meters squared per coulomb squared. And we're going to multiply that by 1.6 times 10 to the negative 19 in coulombs. And we're going to square that value too, because the charge of an electron is equal to 1.6 times 10 to the negative 19. The charge of a proton is the same, so we're going to just square that. And then we're going to divide that by the distance between them, that 5.3 times 10 to the negative 11 meters. And that equals 4.35 times 10 to the negative 18 joules. I left the negative sign out there, so it's really equal to negative 4.35 times 10 to the negative 18 joules. So that's how much energy there is between the potentials of the electron and the proton in the standard Bohr model of an atom. But we want to convert that to electron volts. So if we take our energy that we just calculated here, and we want to convert it to EV, now they give us the conversion rate up here, where 1 EV is equal to 1.6 times 10 to the negative 19 joules. Notice that's the same as the charge in an electron in coulombs. It's an easy way to remember it, at least. So if I take that value, negative 4.35 times 10 to the negative 18 joules, and I'm going to multiply this by 1 EV divided by 1.6 times 10 to the negative 19 joules. Simple conversion ratio, where our joules are going to cancel out, and we're going to be left with the unit in EV. First, we have to divide our value by 1.6 times 10 to the 19. So going back to our calculator, I'm going to throw that negative sign in that I forgot the first time. And I'm going to multiply this by EV. I'm just going to multiply by 1 divided by 1.6 times 10 to the negative 19 joules. And that gives us negative 21.17. So that's going to be the electric potential, or the potential energy is going to equal, I said, negative 27.17 EV. And that's how much potential energy there is between the proton and the electron in the hydrogen atom. So let's move on. Now we have a bit more complicated system here. This one, we're going to have a particle with a charge Q1, which is equal to positive 4.9 microcoulombs, is located at, we'll say, the origin, 0, 0. A second particle with charge Q2 is equal to negative 8.6 microcoulombs, which is located at x equals 0 and y equals 4 centimeters. And the third charge, Q3, which is equal to 4.8 microcoulombs, is located at x equals 3 and y equals 0. So I'm going to draw that out on my grid to begin with. I'm going to highlight my values that are important so I can find them a little bit easier as I go. And we're going to draw a grid. Now I'm going in the positive y and the positive x. So I'm going to draw this guy here and this guy there. And we're going to say the first charge is located at the origin. That's Q1. The second charge is going to be located at x equals 0, y equals 4. So I'm going to go up, say 1, 2, 3, 4. I'm going to put another charge right there. The third charge is at x equals 3, y equals 0. So say that's 1, 2, 3, and this one's going to be right here. Now I can draw a line kind of creating this idea of the triangle. So this is going to be my system that I'm worried about. The charges that I'm looking at, Q1 is 4.9 microcoulombs. Q2 is negative 8.6 microcoulombs. And Q3 is 4.8 microcoulombs. So now I've got my system set up, and that's kind of what part A was asking. In your notebook, draw a diagram of the 3 charge systems showing the location of the charges. But there's my system. And we want to then calculate the potential energy of this system. Well, to do that, we need to first look at the potential energy for each point relative to the other points, right? So we can say that the potential energy let's say this, the potential energy of the first point, right, is going to equal, so let's call this 1, right? This is 2, this is 3. So the PE of 1 is going to equal K QQ over R, right? And I can use, I've got my equations, there we are. There's my equations there. The potential energy equations are now above me. Those are the ones I'm going to be using a lot in this talk. So, and this is of Q1 on Q2, we can say, with the radius of 1 to 2. We're going to have to add to that the same potential energy of Q1 on Q3. So each of these values are slightly different in that Q1 is the charge of Q1, Q2 is the charge of Q2, Q3 is the charge of Q3. R1 of 2, or 1, 2, is the distance between them of charge 1 and charge 2. And R1 of 3 is the distance between charge 1 and charge 3. So to do this, we have to find that potential energy for charge 1 alone. And then we can add that to the potential energy of charge 2 and add that to the potential energy of charge 3 to find the total net potential energy of the whole system. So we can plug in some values here. We can see that it's K. We know what charge 1 is. Charge 1 is 4.9 microcoulombs. We know that charge 2 is negative 8.6 microcoulombs. And we know the distance between them. So this was at 4 centimeters, right? From the origin. So the distance between them is going to be 4 centimeters. I'm going to make a little bit of space here, because we're going to add that to K times the same charge of 4.9 microcoulombs for charge 1, and then a 4.8 microcoulombs for charge 3, divided by the distance between those, which was 3 centimeters. And this should equal the potential energy of just charge 1. We can do that same thing now for charge 2. The potential energy charge 2 should equal Hold on, I'm reading my notes. 4.8, 4.9. That was this divided by 3. Yeah. Q1 to 2, 1 to 3, and Q2 to 3. Oh wait, so they're adding just the idea of adding to this KQ of 2 to Q of 3. So you have the potential energy of 1 to 2 and the potential energy of 1 to 3, and then the potential energy of 2 to 3. So we're adding in, and then we kind of account for the potential energy between all of them. So that would be over R2, 3. So adding that in, we would then add KQ2, which was negative 8.6 microcoulombs times 4.8 microcoulombs divided by the distance between those. And in this case, the distance is going to be the square root of 3 squared in centimeters. I'll say 3 squared plus 4 squared centimeters squared. I just kind of factor the centimeters out of that one, and we can pull it out of the square root altogether. 3 squared is 9, 4 squared is 16, so 9 plus 16 is 25. That's just going to be 5 centimeters on the bottom. So now we can plug this into our calculator. And see what we get. So K, I'm going to factor the K's out of all of them. So that would be 9 times 10 to the 9th power. And that's in newtons meters squared divided by coulomb squared. I'm going to multiply that times be 4.9 times 10 to the negative 6, because they're microcoulombs, times negative 8.6 times 10 to the negative 6 coulomb divided by I want a couple more things there. Divided by the distance between those two, which was 4 centimeters. That's 0.04 meters. Plus 4.9 times 10 to the negative 6 coulombs times 4.8 times 10 to the negative 6 coulombs. Oh no. Divided by the distance between those for the second one, that's 1 to 3 now. It's 0.03. And that's in meters. We're going to add that to the third potential energy for the potential energy for the third point, which is going to be negative 8.6 times 10 to the negative 6 coulombs times 4.8 times 10 to the negative 6 coulombs, all divided by the last one, 0.05. We said 5 centimeters on that last one. I think I have an extra parenthesis in here I need to get rid of, because it needs to distribute that k value out to all of them. There we go. And we got negative 9.8559. So let's see if I 8.6 divided by 4, 4.9 by 3. Everything looks correct. So negative 9.85. So the potential energy of the whole system is equal to negative 9.85 joules. So it's really just adding up the potential energy for each point and then summing them all up together. And go on to another problem. This one's similar. We're going to find the amount of work an external agent must do in assembling these charges around in this square grid. There's 4 charges here. There's a 2 microcoulomb, a 3 microcoulomb, a 4 microcoulomb, and a 5 microcoulomb, all kind of going around in a circle or in a square. I'm going to assign numbers to these to make it a little easier. This is going to be 1, 2, 3, and 4. So to do this, we have to bring these in stages. The work to bring one charge in, then the work to bring that second charge in, the work to bring that third charge, and the work to bring that fourth charge in. So the work to bring that first charge, let's start, obviously, at the first charge. When we just put this other charge in, none of these other charges are there yet. Just this guy's all alone. So there's no force acting on it at all. It's just a free-floating particle that's charged and it's happy. Nothing's around it. So the work for that is going to be equal to 0. For the second charge now there's another particle in the vicinity. So there's going to be some work there. And that work is going to equal to K, Q1 to Q. When you're bringing in that second charge, it just has charge 1 there. So it's Q1 to Q2 divided by the distance R1, 2, which in this case is equal to 9 times 10 to the 9th Newton meter squared over Coulomb squared times the charge of 1, which is 2 times 10 to the negative 6 coulombs, times, we'll say 3 times 10 to the negative 6 coulombs. All right, so they're both positive charges. In fact, all of these are positive charges. So we're doing 2 times 3. We're going to divide that then by the distance between them. In this case, the distance is 1 centimeter. So I can say 1 times 10 to the negative 2 meters. And we can plug that into our calculator, find out the work for just bringing in that second charge now. So that was 9 times 10 to the 9th Newton meters squared divided by Coulomb squared times, and it was 2 microcoulombs, so 2 times 10, oops, wrong button. 2 times 10 to the negative 6 coulombs times 2, let me put the times here. Yeah. There, extra parentheses in the right place always helps. Times, it'd be 3 times 10 to the negative 6 coulombs, and we're going to divide that whole thing by the distance between it, which is 1 times 10 to the negative 2 meters. And looks like everything's good. I always like to double check. Coulombs are going to cancel out. Meters will cancel out. We'll have Newton meters. And let's enter. Oh no, I left the L off. Now we got joules. That's better. 5.4 joules. So going back here, this is going to equal 5.4 joules. And that is the work for the second charge, to bring that second charge in. The third charge, this one gets a little bit more complicated. With that third charge, we're going to have to add in the force of two different charges working on it, because it has to do work from both of those to get in there. So that work is going to equal K Q1 Q3 over R13 plus K Q1, or say Q2 Q3 over R23. So that's going to equal, I'm going to factor the K out and the Q3 out just to make things easier. That's K Q3 times Q1 over R13 plus, well, let's just write in the values for them. We're going to run out of space. 9 times 10 to the 9th Newton meters squared over Coulomb squared. That's your K value times your Q3. So Q3 was 4 microcoulombs. So that's 4 times 10 to the negative 6 coulomb. And then we're going to multiply that by Q1, which is 2 times 10 to the negative 6 coulomb, divided by the distance between Q1 and Q3. In this case, that's going to be the square root of 1 squared centimeter plus 1 squared centimeter, which is equal to the square root of 2 centimeters. Because we can, I'll just do it right here, 1 centimeter squared plus 1 centimeter squared. Take the square root of that. I can factor out the centimeters squared outside of that and get centimeters squared still underneath the radical. Pull the centimeters out from the radical and I have 1 plus 1. So it's just the square root of 2 centimeters. And that's the distance here between these two here is going to be root 2 centimeters. And that was from 1 to 3. So then we can do plus that, add to that the charge of 3, which is Q2 is 3 times 10 to negative 6 coulombs divided by 1 centimeter. In this case, I'll change the centimeters to times 10 to the negative 2 meters. I always like to work in meters if I can. And that should do it. We just got to plug it into our calculator and find out our result. So this is going to be 9 times 10 to the 9th power Newton meters squared over Coulomb squared, which is times 2 times 10 to the negative 6 coulombs. I lost my times 10. Times 10 to the negative 6 coulomb divided by, and then our distance there was square root of 2 times 10 to the negative 2 meters. We're going to add to that now the 3. So that's 3 times 10. This is Q2. 3 times 10 to the negative 6. That's microcoulombs. Divided by the distance between that and Q3, which was 4 times 10. or sorry, 1 times 10 to the negative 2 meters. And I left out one value here, which is our Q3. That's 4 times 10 to the negative 6 in coulombs. There we go. So I have K times Q3, which is then going to all be distributed into this Q1 over R13 plus Q2 over R23. And that equals 15.89 joules. Let's go back here. Let's say 15.9. Move that up there. And so that's the work it takes to move that third charge in. We've got one more charge left. This one gets just a little bit more complicated because now we have 3 other charges. So we're going to do that same pattern that we had. We're just going to have one more term inside there. So finally, the work here is going to be KQ1 on Q4 over R14 plus KQ2 Q4 over R24 plus K Q3 Q4 over R34. And this is going to be equal to 9 times 10 to the 9th Newton meter squared over Coulomb squared times the charge Q4. I like to factor it out so I don't have to type it in 3 times over, which is 5 times 10 to the negative 6 Coulomb. And then we're going to multiply that times Q1, which is 2, times 10 to the negative 6 Coulomb divided by the distance between 1 and 4, which is 1 centimeter. So it's 1 times 10 to the negative 2 meters plus 3 times 10 to the negative 6 Coulomb, which is Q2. Okay, and we're going to divide that by the distance between those, which is the distance, the same distance we had from 1 to 3, because it's a square. So we don't have to calculate that again. We know it's square root of 2 centimeters, or square root 2 times 10 to the negative 2 meters. We're going to add to that charge 3, which is 4 times 10 to the negative 6 Coulomb, divided by the distance there, which is 1 times 10 to the negative 2 meters. And this will give us the work to bring in that last 4th charge. So that'll be 9 times 10 to the 9th. We're going to still be in newtons times meters squared divided by Coulomb squared. We're going to multiply that by, it would be 5 times 10 to the negative 6 coulombs times, it would be Q1, so 2 times 10 to the negative 6 coulombs divided by the distance, again 1 times 10 to the negative 2 meters plus 3 times 10 to the negative 6 coulombs divided by, this one's going to be square root 2 times 10 to the negative 2 meters. I left it meter out. We're going to add to that the 4 times 10 to negative 6 coulombs divided by the distance there, again, is 1 times 10 to the negative 2, and that's between charge 3 and charge 4 in meters. And we should be all set. And gives us 36.55 joules. So this one is 36.5 I'll just say 36.6 joules since I'm a little bit out of space, and 3 sig figs is fine for what we're doing. Notice that the work it takes to add more and more charged particles in here increases the every charge we add. The first charge was 0, the second charge was 5.4 joules, so it didn't take a lot. The third charge took 3 times as much as that, and the fourth charge took double what the third charge took. So it's ever increasing every time. If we were to add more charges in there, that next charge would take even more, because you would be having force for each of these being added in there, or work from each charge before adding in there. Now we need to add the total work together, so that's the work of 1 plus the work of 2 plus the work of 3 plus the work of 4. When we add all those up, luckily I have them saved on the calculator here. So the work of 1 was 0, so the work of 2 is this 5.4. The work of 3, the work of 4 is all in there, and the total is going to be 57.83 joules. Yeah. 57.83 joules. So that's the total amount of work it takes to move 4 charged particles into a 1 centimeter grid around them with those charges there. Okay, this is going to be the last problem. There's a couple stages to this problem here. We have an evacuated tube, uses an accelerating voltage of 55 kilovolts to go. Here we're talking about more voltage potential here. So like the idea that between around a charge point, there's a potential for energy at any one point. It's kind of similar to the idea of an electric field versus a force, but in this case, it's instead of potential energy, we have voltage. So the potential energy in this case is going to, the change of potential energy is equal to Q times the change in voltage. Or the negative work from A to B is going to be equal to Q times the change in voltage. So in this situation, we have an evacuated tube, which is like a vacuum basically. And it uses an accelerated voltage of 55 kilovolts to accelerate an electron's hit to hit a copper plate to produce X-rays. So if we had, I'm going to draw a diagram here, kind of a one plate here, we had another plate here, there's like a gap basically, there's another plate here. We could sit an electron. There'd be electrons all over there, but there'd be one that's kind of lined up just right, where when the electric field from positive to negative comes in, and it's got a uniform electric field going down, the voltage between there is going to accelerate this electron, and that electron is going to shoot out that way. Excuse me. And in this case, the voltage potential between those plates, between the charge of that electron and that charged plate, the potential energy is going to turn into kinetic energy and launch that thing. And if it happens to make it through this slit, it's going to go flying. And we can calculate the potential energy that we have here based on the amount of work that's being done. So in this case, we want to use the idea that work is equal to negative Q VAB. Okay. Where VAB is the voltage difference between points A and B, and the work is going to be basically how much work is being done. So we can determine that work because they tell us, okay, and we can use the idea of the, did I not put the, what they didn't tell us on here, which I should have written down, is that there is, oh, it's 55 kilovolts. That's what it is. That 55 kilovolts is the voltage potential that's going down there. And the charge of that electron is going to be the 1.6 times 10 to the 19. So if we write that, the work here is equal to negative of negative 1.6 times 10 to the negative 19 coulombs times 55 kilovolts. That's 55 times 10 to the third volts. And if you remember, volts is really another term. Volts equals joules per coulomb. So we can substitute in here. I like to follow the units, make sure the units work out, because ultimately work should equal joules. Work should be a form of energy. So the coulombs will cancel out unit-wise, so we'll be left with joules at the end. And that's good. I like that. So plugging this guy into our calculator, find out the work being done. So that's negative 1.6 times 10 to the negative 19. This is going to be in coulombs. And it's really the negative of that, because we have negative Q VAB. So I need a negative in front of that too. So that answer is going to be positive. And we're going to multiply that times 55 kilovolts. That's 55 times 10 to the 3 volts. And we get 8.8 times 10 to the negative 15 joules. So that's equal to 8.8 times 10 to the negative 15 joules. So it's not a lot of work, but it's enough to get that thing going. And we can find the potential energy there if we were to say just the relationship where work is equal to the negative change in potential energy. So it's really just the negative. So change in potential energy is equal to negative 8.8 times 10 to negative 15 joules. Okay, so that's gives us our potential energy. This is the work being done to excite this electron out. So it's kind of accelerated away. The next part of this problem is an electron to be accelerated in a uniform electric field having 2.3 times 10 to the 6 volt meters. So this is the same idea. We're accelerating this electron in a unified field. And the electric field they're giving us is 2.3 times 10 to the 6 volt meters. Now volts per meter, is just another way to say newtons per coulomb. Because we know that we can go through all the unit analysis, but if you see this, just think electric field. If you see this, think electric field is the idea. So we can calculate this because we know the change in kinetic energy is equal. They want us to find in here what energy in keV is given to the electron if it's accelerated through this much, 0.3 meters. So we want to find out how much energy the electron's given. So we have the electric field and the distance. We should be able to figure out the kinetic energy from that, because kinetic energy is equal to the negative delta PE. Delta potential energy is equal to negative QV, and we can say KE is then equal to Q delta V. And we know that delta V is equal to the electric field times the distance. And we can see that in the units. If I were to multiply this by some type of meters, we'd get voltage through there. Right, where V over M is the electric field. So I can calculate that first, saying this is going to be 2.3 times 10 to the negative, or to the 6 volts per meter times 0.3 meters. 2.3 times 10 to the 6. 2.3 times 10 to the 6th power, and this is going to be in volts per meter. I'm going to multiply that 0.3 meters. We end up with 6.9 times 10 to the 5 volts. 6.9 times 10 to the 5th volts. If we were to then multiply that by Q, so we can find the kinetic energy, Q in this case, it says an electron. So Q is going to be negative 1.6 times 10 to the negative 19 coulombs times our 6.9 times 10 to the 5th. Yeah, and we could leave the negative out, I think, because in this case we're just talking about the magnitude of those. Kinetic energy has, it's more of a scalar value, not a vector. So in this case, multiplying that by 1.6 times 10 to the 19 times 1.6 times 10 to the negative 19 coulombs is equal to 1.104 times 10 to the negative 13 joules. While we're here, we might as well convert it to EV. So this times 1 divided by 1.6 times 10 to the, it really just goes back to what it was at before. So we'll see that times 10 to the negative 19 joules in this case is going to be back to 690 kilovolt EV. So just to add what I did here, this is 1.6 times 10 to the negative 19 in joules, so we can get EV, and that would be equal to 690 kilo EV. There's 1,000 EV per kilo EV. And unit-wise, this and this, we're not just kind of canceling those out. We end up with coulombs over joules. Oh, this was volts, that's why. Volts. And that's our answer. That's how much energy is put into launching that electron out. If it's accelerated 0.3 meters at an electric field through an electric field of 2.3 times 10 to the 6. I think I might have a little bit more time to run through this last part. At what distance would it have to be accelerated to increase its energy by 47 giga EV? So I'm going to calculate how much energy is needed to accelerate it to 47 giga EV. So just to do some unit conversions, 47 giga EV, that's going to be equal to 10 to the 9 EV per giga EV. Okay, and I'm going to convert it to joules because that's 1.6 times 10 to the negative 19 joules per EV. And that equals, if we plug 47 times 1.6, you get 7.52 times 10 to the negative 9 joules. So this is how much energy we need to accelerate our electron by. Using that same idea of the equation, the delta KE is equal to QED, right? Where we have the same electric field, we have that same Q, the electron, we need to find D, so I can say that delta KE, which needs to equal this value here, divided by our electric field and our charge of the electron needs to equal that distance. So we can set that equal to 7.52 times 10 to the negative 9 joules. Divide that by our electric field, 2.3 times 10 to the 6. It's V over M. And then multiply, or also divide it by 1.6 times 10 to the negative 19 coulombs. If we plug that in, 7.52. So that was 7.52 times 10 to the negative 9, right? Yeah, joules. Divided by 2.3 times 10 to the 6. Yeah. And that was in volts per meter. I'm going to multiply that also by 1.6 times 10 to the negative, double negative, single negative, 19 coulombs, the charge of an electron. And that gives us looks like 20,434.8, or about 20.43 kilometers. So that's 20.43 kilometers. So that's the distance. That's how far we would have to accelerate this electron in that same electric field to get it up to that 4.7 giga eV, which is a really large eV. Getting to the point of like electron scanning microscopes at that point. So I hope you all had fun. That's all I have for you today. I'm going to again post a link to our attendance sheet. Make sure to fill that out if you're here, get some credit, and I'll see you next week. I also have drop-in hours through Penji. You can schedule an appointment with one of our tutors, or just go to Penji and drop into the drop-in hours. I'm there from 4:30 to 5:30, and I'm happy to help you out with any questions you might have on this or anything else. Have fun.